not GPUs are the best platform hardware parallelize this algorithm, but we will think about how we can improve, for example, the memory usage on that. So that can be a future plan.
That's nice. Thank you.
Thank you very much.
Then let's jump to the next lecturer with Péter and Naszvadi. Yeah, and thanks again. And he's going to speak about his reduction and efficient solution of MILP models of mixed Hamming packings yielding improved upper bounds. So nice and long title.
Microphone próba. Oh, thanks. Good afternoon, everybody, and thanks for the opportunity that I will show up what we did in the last year with the Ignition Center and the GPU level. VSC lab provided us some technical stuff in order to make some calculations. I'm Péter Naszvadi. I'm a PhD student at the University of Felta, and my PhD supervisor is Mátyás Konyolcsik, a physicist. And I'm going to talk about some results, including some theoretical ones, as well as some computational ones, about classical Hamming packing. Imagine an outline. First of all, I'm going to say something about the noise intermediate scale, the quantum devices, basically the easing the type annealers, and then I'll show up some of the DQP modeling methods as well, which is strictly related to the easing quantum computers as well. And it will turn to classic mathematics, code theory, and external commentaries, Hamming packings, what's it, why is it relevant for us, and why it will be in the future, and some developments and results and discussions, conclusions at the end part of this presentation. The easing model is a type of a quantum computing model, which is basically this energy function is being optimized when the parameters are the Ji Hamiltonian and this magnet rep, which is a linear part. This is nothing but a global optimization over a constraint set, which is these are discrete variables, and this energy function is about to be minimized. The physical background is more or less well known in this institute and so on. And you can read more about it here. So quantum annealing. What is interesting for us, we need to benchmark somehow these kind of quantum computers. And there is a stipulation of discrete optimization problem, namely the Q-board, which is nothing but quadratic, unconstrained binary optimization problem. Imagine that a given problem is defined by this quadratic matrix. This could be arbitrary, and this quadratic form, which can be even indefinite, positive or negative summit, and so on, convex, non-convex, whatever. It is optimized on these discrete variables. I do not recommend to solve it with embedded for loops because the all-time EOS won't be enough even to evaluate n-hydrogen times n-hydrogen sized matrix, which is usually can be found amongst the de facto industrial standard benchmark problems nowadays. One can transform the so-called Cubo model to Ising model as well, and the Ising models Cubo is vice versa. Silently, I remarked that Ising models is basically nothing but so-called max-cut graph theory, max-cut problem from the graph theory, in order when the maximal cut is about to find in an ordinary weighted matrix, after removing the linear part, which can be done efficiently. Now, what is Hemming packings? Richard Hemming, a famous code theorist, made some stunning results. And the discrete mathematical problems. What is Hemming packing? For example, let me show this side. Imagine that we have this type of basic elementary set. These elements of this H set is a Cartesian product, and these elements are called words. And this is also a topological space where the topology is induced by this metric, and this metric is continuous, obviously. And this metric is nothing but we summarize the positional wise differences for each code word. There are different types of discrete metrics in code theory. For example, this is the Levenshtein distance. This is typically difference from the Hemming space. These code words considered as strings have a Levenshtein distance 2. Just remove this 0, and then extend this code word with 0, obtaining this one. And these tuples Hemming distance is 10, because in each consecutive pairs, which is zipped, all differs from each other. And the Hemming packing is a maximal subset of H with a fixed given D, which is a natural number, usually strictly bigger than 0 and strictly less than the number of participating sets in this Cartesian product. And to get confused, we also denote this Hemming distance with D, and this constraint should stand that for every different code words in the selection must hold this inequality. So it must differs in at least D positions. And this is a cardinal problem in several areas. For example, football core systems, generalized football core systems, telecommunication protocols, quality assurance, and data compression, and so on. This gives its importance. And the key question is to determine this NH for a given Hemming space and a given D. These notations are well known and spread in the literature. This is just for confuse the reader who might be interested in the after this conference when obtaining one. So a binary program, a classical linear program to determine this NH value is this objective function, which is summing these truth variables. And we define these truth variables is assigned to each code word in the Hemming space. If it is, this is one and only, if and only if it is in the our maximum Hemming packing selection. And these are the so-called mutex constraints. So every code pair, which is differs, but so close each other, they cannot be chosen together. And as I mentioned before, the truth variables are denoted with 1 or can be this domain. The properties of this model. This ensures the maximality, which to be correct, and the corresponding Cubo model is so straightforward. What we've done, a decomposition. Before our work, I never proposed anyone to determine such n values using linear programming. But after that, this is the corresponding QO model, where Q is a so-called upper triangular matrix in which the diagonals are the negative of the identities. And the above diagonal elements are given fixed positive penalty, usually must be chosen strictly greater than 2. So theoretically, it is an optimal solution. But the devil is in the details, which is far beyond to this presentation. So there is a rich literature about classical Hamming packings. And this is our key task, and to ease its sum. This is our first theorem. Is it preprint already and probably doesn't contain any errors. Hopefully it's checked by the mathematicians as well. So every Hamming packing C with a given minimal distance can be transformed to another Hamming packing with exactly the same cardinality, containing the same number of code words and whose contact graph is connected. And we should define the so-called contact graph, which is inherited from the continuous sphere packings from the classical Thomas problem. And it is not trivial to use it in this discrete sphere optimizations. There are some interesting and very useful corollaries when we are trying to optimize this, on this problem. So that can be some custom specific ball squeezing constraint to these kind of models. And the maximal codes having at least a matching or some special types of graphs. And additionally, several code words can be forced in. So before we starting the real calculations, some words can be removed. This is a little bit graphic with an ambiguous meaning. And basically, this is the key algorithmic proof of the used down paper. And this is the contact graph from the famous Thomas problem. This is a simplified model when there is a given number of points, usually flowers and some particles on plants, and they are about to be arranged as dense as possible with a given cardinality. Whilst there's a minimax problem when the minimal distance which takes place must be a maximal one. And the contact graph is when the S sign for each specific subsets, in our example, the C. And this contact graph structure for every code word, the S sign graph, its vertices should be these, and the edges between two different nodes, if and only if they have the so-called Hamming distance D. This is the contact graph definition. There is a second lemma, which is much more useful when we have a very dense alphabet. For example, if in every place there is a minima as of this k indices is 3, which means that every code word in every position has at least 3 elements. In that case, the so-called contact graph for the maximal Hamming packing, there exists such a maximal Hamming packing with a contact graph in which every node has a degree at least 2, which means basically it has many edges as well. So let's just jump to the proof and the figure sketch. Imagine that we have an algorithmic proof, and this is the maximal element, and this is indirectly. Suppose that we have this maximal Hamming packing in a special properties with the Hamming packing with special properties in which every alphabet can be chosen in at least 3 elements. Every alphabet, every Cartesian product member has at least 3 elements. So in that case, suppose that we have an orphan edge of not an orphan, but a vertex which has a degree 1. In that case, it has a Hamming distance from these at least D+1 due to this property. And this code word, which shouldn't be selected due to the maximality of these the continuous delimited rectangles, unions. This shouldn't be a member of the chosen set. This has at most D-1 distance from these elements. And the key observation is the proof when we change these twos one from left to right without a loss of generality. You can suppose that these elements has this form due to symmetrical reasons, and for every step the Hamming distance of this element from these changes at most 1. So there should be at least one element somewhere this, which has a Hamming distance exactly 1. This means that this element could be replaced with this, whilst improving our selected code word subset. And these node, for example, will have a degree in this contact graph at least 2. So results. This is a very incomplete list. We tried to run and modeled more than 2,500 relatively small models. So burned the CPU, and some of them obtained some already known set records as well. For example, let me see this running. This means the running time is seconds, and this is the memory consumption. We got a node having 256 gigabytes of RAM. So it's hardly enough to fit because it had other workers nodes on it. And we solved this Hamming packing, which means no one can select more than 24 or at least 25 elements from these. And this running take 10 more times, about how many seconds? More than 10 days. Wow. In this, we shut down because it was a OM killer did what it do. And after then, we applied the trick, added one constraint, which was an upper barrier of the objective function, the 29. And calmly, silently, the branch country had been emptied, proved that the best value is 28 for this problem. Other conclusions. These records had been set, and these records had been also provided by Patrick Östergand and forgotten for almost quarter century, but we rediscovered it. It is a long story. And there is a more or less up-to-date records for these kind of Hamming packings and external structures as well, maintained by Andreas Gruber. And this is a very strict method, basically equivalent with proofs. So it is approved by the mathematician community. These kind of enumerations are truly equivalent to the exhaustive searches. Still needs exponentially many time, and sometimes exponentially many other kind of resources like RAM, as you can see. So this is a caveat. A reliable GPU support of the mixed integer linear programming solvers is still a challenge. Painfully, it is wanted to support by upstream solvers as well as including open source ones. And low-hanging fruits have been picked. Is about to be published. And this is our preprint, published in last October. Now something about the D-Wave. This is a quantum computer on which we have some quantum processing time. And we ran these models. These are so minuscule one, but and showing that this one almost obtained the best known record, which is turned to be the optimal one. And we had to measure this. And we did it. So from a quantum side, we did the right decomposition from which means that we can provide for anyone from now much more smaller, yet to be and benchmark models for quantum, these kind of quantum computers. The well-known models floating around in the easing benchmark community is about 800 times 800 size. This is the smallest ones, not counting the minuscule ones, which is can be solved now. And our hard to solve models usually begin. The smallest one is about 200 times 200, and not so dense. We set this record again, and this is interestingly. We ran with a hybrid D-Wave solver, and it's almost Optima is being fed as a MIP start option to our commercial solver, and with this also it can enumerate in all cases and proved also that this Hamming packing, an 8-length code word and the 7 alphabet, 7 members of the Cartesian products as a cardinality of 2, and the other one, the last one, has a cardinality 3. One can select not more than 26 code words in tuple. Every code word pair, a different code word pair differs in at least 3 elements. And such packing models scales automatically according to the quantum Moore's law. So most quantum models are obsolete to the time. However, different models according to the scale and parameters, knowing that these models can be solved very efficiently with classic methods, and their QUBO forms are still will be in the future very rude and very difficult to solve quantum models. And before the questions and answers section part, I would like to thank the Development Innovation Office in the Quantum Information National Laboratory at Hungary and the VSC Lab for providing us this kind of CPU time and hardware.
Thank you very much. Is there any question?
No gamblers, no football pool players. Oh, I want to gain so much money.
Why do you choose the D-Wave quantum computer, and do you think about testing this algorithm on others?
This is not a QAOA based, this is a Z-Zing based. And the model was selected, not just roughly on this, because these models has a so-called mutex type constraints. So there's also rich literature how to model problems with the integer programming. There you go. Right. And these kind of constraints are the only ones that can be modeled with QUBOs without adding any special helper variables or helper lines or columns as well. That's why we chose using QA is a different case. Though allegedly QA can solve different kind of NP-hard problems.
If there are no any other question, let's thank again for the presenter. And our last but not least speaker today is
Balázs Kackovics is going to speak about gravity waves, right?